Thank you very much, Mr. Chairman. It's my pleasure to be here, ladies and gentlemen. Today I will to give a talk on the effects of defects and microstructure on the high cycle fatigue of selective laser melted TC4. Firstly, I would like to give thanks to my students, my PhD students, Nai-Jian and Kang-Kang. And thanks also goes to Professor Chen, who is from University of Leicester and is now working at Southampton, UK. And I would like to appreciate the help by Professor Shan-Tung too at ECAST. This is the outline. First, I would like to introduce the motivation of this study, and I will briefly introduce the material and the experimental procedure. Then I will give some results of the tensile and high cycle fatigue behavior of the TC4. And we also explored the high cycle fatigue mechanisms and the high cycle fatigue prediction models. And finally, we'll get some conclusion. As we all know, the TC4 is the most widely used titanium in the world. It has been successfully used in the area of aircraft and jet engines because of its low density and high strength. And nowadays, the additively manufactured TC4 are also widely used in many applications, including the Airbus cabin hinge brackets, the engine parts for spacecraft, and also the customized bio-alternative structures. But all these applications require very high cycle fatigue life, let's say more than 10 with the 6 power cycles. And we know that in the AM materials, the anisotropic microstructures and defects cannot be ignored. And because this kind of two things it affects the fatigue life very much. But there is no, very solid conclusion right now. For example, we cannot judge directly which direction is better. For example, for the study by Beihang University recently, they found the better direction would be the horizontal orientation. But for the same material from BIAM, they said the vertical orientation would be better. So people also use post-processing to enhance the fatigue properties, and because they can change the microstructure and also the defects in the material. But right now, the combined effects of microstructure and defects on high cycle fatigue fracture remains unclear. And for the high cycle fatigue life prediction models, we do have several very nice models considering the effects of size, location, and shape of the defect, and also the microstructure. But the defects feature-based models considering different microstructures need further study. So the purpose of our study, one of them is that to explore the combined effect of anisotropic defect morphology and intrinsic microstructure on a high cycle fatigue life. And we also would like to develop a fatigue life prediction model considering the both effects of microstructure and defects. And this is the second part. And we have this kind of attributes TC4 material from UK by Professor Chen-Bo's group. And we obtained the samples of fatigue samples and tensile samples from this bug. And the features of our study is that we use three types of post-processing methods. The first one is called stress relief. The process temperature is 550 degrees centigrade, and the duration is 2 hours. The second one is called sub-chances. The temperature is elevated to 920 degrees C, and also for 2 hours. And the other one is HIP. So this is the defect and microstructure after 3 types of processings. We can find that for the defects, for the SR and sub-chances, there are still some defects inside the materials, but after HIP, there's no defects. And for microstructure, for the SR and sub-chances, for the SR, we can find the main phase is the alpha prime martensites, but after the sub-chances and HIP, we can find the phase is mainly the alpha plus beta phases, and the width is become larger, and the beta phase is in the range of about 10%. And we also use XCT to see the differences of defects between different treatments. So for SR and sub-chances, we can still see the defects of lack of fusion, and this is the orientation of the defects and the size of the defects. And we can see the long axis of the LOF is almost vertical to the build direction. And after HIP, the porosity is reduced from 2% to a very small value. And we can also see the SR and sub-chances states has the almost same morphology of the defects, because both of them are without additional pressure on the specimen. And I don't go to the detail of the EBSD, but we can find the weaker texture for the sub-chances states and strong texture for the HIP state. And this is the experimental equipment we are using and the specimens of the tensile test and the high cycle fatigue test. So let's see some results from the test. On the left-hand side figure, we can find the SR state has the highest strength, but the material become very brittle. For sub-chances and HIP states, we have a similar yield strength, but the ductility of the material become better than the previous one. And this is how we define the defect location and the area of the defect, because we would like to use this kind of parameters in our models. So this is the results of the high cycle fatigue data, and we can find the sub-chances results are for a given stress amplitude, the sub-chances give a higher fatigue life, and the HIP one is the best, because the fatigue strength has been raised from about 120 megapascal to more than 280 megapascal. So let's see the fatigue mechanisms. We find that there are 2 cracking modes for the different processing states. The first one is called defect cracking. This is for the SR and sub-chances treatment. And the other one is called facet cracking. This is for HIP states. We found the defect has been eliminated by HIP process. And so the defect cracking has been transited to micro cracking because there are no defects at all after HIP, and the fatigue strength has been raised by about 2 times. So this is the HIP's function, and we also find there are difference between SI and subtransit samples. The essential thing is that we found the localized micro crack growth defects under subtransit states, which is not in the SR states. And this kind of micro crack growth actually extends the crack initial time for the subtransit states, which also leads to the higher fatigue strength. And for the HIP states, there is no defects. The cracks initiate in some microstructures, and the cracking model can be further divided into 3 types. The first type is called hard soft grains, and the other one is called soft grains. And the worst one is type 3, because this is due to the cluster of this phase. So the contribution of HIP is limited by the cluster caused by the very high temperature. We can see the symbols here for the type 3. It always has the lowest strength. So the last thing is about the life prediction. Actually, we would like to solve these 2 challenges. Okay, I will be quick. We already have some models in the literature. For example, it's called parameter model. But unfortunately, when we use this model for our material, a very poor life prediction based on cracking source size in microstructure cracking mode. For example, the error bounds can be as high as 70 times. So we use the very simple tensor properties like the fracture elongation and yield strength, because we find the fatigue limit is very very much relative to these 2 properties. So this is our model, and we actually reduced the error very much. And this is the conclusion. I don't want to read it, but I would like to give a short advertisement about a conference, ISSI 2024, and it will be held in Guangdong, China. And this is a very long history conference, and it will be held in November 5th to 8th, 2024. And we already have some very distinguished professors to attend our conference, including Professor Reddy from Texas A&M, Professor Robert Smith from Imperial College London, and Professor Loca from Spain, and Professor Konstantin from Oxford, and our ESIS chairman, Professor Sedmak, will also come. And we are looking forward to your visit. Thank you so much.
Thank you.